Yeah, there's supposed to be an insulator board behind that circuit board, and after reassembling this thing and doing all the tests that you see in this video, I went back and took it all apart again and put that insulator back in. Hello Internet, my name is Quinn and this is Blondihacks. Have you ever wondered what's inside those import power feeds that are ubiquitous on Bridgeports and also smaller mills? Well, mine needs a little tune-up, so I'm going to take it all apart. I'm going to show you how it works, and we're going to make it work a little better. So let's go. Here's the electric power feed on my mill. It's pretty standard for electric power feeds. It'll feed one way, and then when you disengage it, the motor spins down, but the table stops immediately. And then when you feed the other way, same thing. And then of course there's a button for rapid travel. And once again, it's very important that when you shut that lever off, the table stops immediately so that you don't crash the cutter into something. I know very little about how this thing works, so I don't know what I'll find in there. I do see ports for brushes, so presumably it's a DC motor. So I'm expecting to find a rectifier in there because it runs off AC, and I'm expecting to find a flywheel under that big rectangular cover there. Now you can see here how it works, and it seems okay, but listen to what happens here. You hear how it's kind of laboring and slowing down? It does that only in one direction, and it's been getting worse to the point where it's actually stalling sometimes during a cut. And furthermore, this is about as slow as I can run it, which is really too fast for some cuts, like for a fly cutter, for example. Now, it's got lots of power. You can't stall it with your hand when it's running slowly like this, but it stalls anyway, so I think the problem is more electrical than mechanical. So let's take a look at this thing. I'll start by unplugging it so we can work on it safely. Here's how it mounts on the Precision Matthews mill here. There's a couple of bolts here that have hardened points on them, and they hold this bracket to the end of the table. Now, I don't love this arrangement. As you can see, it blocks the ends of the T-slots, so you can't get T-nuts in and out. Not ideal, but it is inexpensive and easy to install, I guess. I could mill some clearance there, but my solution is to keep extra T-nuts down at this end. But rather than disturb the main bracket there, I'm going to take apart these other bolts here. The bracket is in two pieces here, and this part is slotted so that you can adjust the backlash on the gears. So loosening those allows me to lift the whole assembly off, and now you can kind of see how this works. There's a sheet metal guard there for the gears. I'll get that off, and now I think you will recognize this thing. Now, as you can see, it's the same kind of power feed that's hanging off every Bridgeport this side of the Pacific, but this is an import clone of one of the original electric Bridgeport power feeds. So on a full-size mill, this would be hanging straight down off the hand wheels as you see it in this orientation, but on these little import mills, they just create these cast aluminum brackets that you see to mount it horizontally. Let's see if the problems that I'm chasing reproduce here. Yeah, you can see how it runs much quicker in one direction than the other. It's hard to reproduce the slowdown effect. That may require a load on it, but, well, we'll take it apart here anyway and see what we can see. So I have no idea how to take this thing apart. I don't have any kind of drawings or anything for it, but I'll just start by removing the topmost fasteners that I can see, which is this plastic cover. And, well, would you look at that? I was expecting a flywheel under there, and instead there's a large plastic gear. So that's interesting. Already this thing does not work quite the way I expected it to. Well, more fasteners here, so let's get those out of there. There's some big cap screws that are almighty tight. I suspect Loctite in there. And yep, there is indeed Loctite on those, and a lot of grease for some reason. We will soon learn that everything in here is covered in grease for no good reason. Let's see if this will separate now. Oh, we got some movement, but it feels like something is hanging it up here. I don't want to pull too hard. There might be wiring or something in there, so get out my light here and snoop around in there, see if I can figure out what's causing it to hang up. A little more wiggling and a little more progress, but still something in there. It looks like it might be the wiring that goes to the rapid switch, so I'll feed some slack there, disconnect that and feed it down a little bit. The connector won't fit through that grommet, but now we have just enough slack, and conveniently there's a connector here on the circuit board. So that was all we needed, and out comes the guts of the beast here. Let's take a look at this thing. There's a terrifying almighty spring in the top section there, clearly related to the clutch mechanism. I'm glad I didn't put my eye out with that one. And you can see now how the mechanism works. So this is actually pretty clever. Let's take a closer look at this. So no matter which way I move the handle, that armature moves up because there's a little cam in there. So whether you move it in forward or reverse, the cam always moves up, and that creates the mechanical engagement of the motor to the gear train. And that's really the key, because you have to mechanically disconnect the motor when the power feed is not active. Otherwise, you're hand cranking against the motor. And also, you need to make sure the table stops dead as soon as you disconnect it. So that clutch is what does that for you. So in the top half here, that's half of a dog clutch, and then there's the bottom half of it there. So it's a basic dog clutch, and that's why you hear that clunking noise when it engages and disengages. Now what's interesting here on the underside is you can see this really tiny pinion, and that's straight through from the motor shaft, and then that teeny tiny pinion is turning this giant nylon gear. And so that's really all the gear reduction on the whole thing. I expected a little more of a gearbox in here, but nope, just one giant gear reduction. And then here we've got the electronics board. Now this is interesting. That's a neon bulb. More about that in a minute, because that's actually really interesting. But the circuit board is attached to the side of the plastic motor cover there, which has just been self-tapped in there pretty ham-fistedly. So I'll get the circuit board out and let's take a look at this thing. My jaw hit the floor when I saw this circuit. Of all the designs that I thought I might find in here, this was not even on my list. Pause the video here if you're an old school analog electronics person and see if you can identify that circuit. Do you recognize it? This is the kind of circuit that you would find in like Radio Electronics magazine circa 1965. The giveaway is the neon bulb. Now that is not an indicator light of some sort. That's just a neon bulb inside the case that will never see the light of day. Now that is a very old school trick. This is combined with this silicon controlled rectifier, and it's basically a really crappy DC dimmer switch. Like imagine a dimmer switch on your lights if your lights were DC. If that SCR was a triac, this would in fact be an AC dimmer. Very briefly here then, the SCR is rectifying the AC into DC, but it's also acting as a stable multivibrator, so it's creating an oscillator to control the effective voltage applied to the DC motor. Now the trick with an SCR or a triac is that you need an activation voltage and then a sustaining voltage. Normally you do that with something called a diac or a trigger diode, but those are kind of expensive. But here's the thing, neon bulbs, as it happens, have a striking voltage and a maintaining voltage, so they have a profile kind of like a diac, but it's asymmetric and not very reliable, and it changes over time. However, it is a quick and dirty substitute, and that's what they've done here. Now the trick though is that a diac is symmetrical in both directions on the current, but a neon lamp is not. So I bet you anything that is why this thing runs faster in one direction than the other. It's because they saved a few pennies by using a neon lamp instead of a proper diac. Now the neon bulb does glow ever so slightly while doing this double duty, so they've very optimistically put it in the corner of the PCB, and there's a little light pipe on the outside of the case so that this bulb can also act as a power light, but it's so dim that you really can't even see it. Now other interesting parts here, on the side there you see a giant 10-watt wire wound resistor. When you rectify that AC mains down to a stable vibrating DC, all that extra current's got to go somewhere, and it's going into that thing. So dollars to donuts, if you ran this thing at low speed for long periods of time, eventually that thing is going to cook itself. Now 10 watts is a mighty resistor. That's basically a small toaster oven, but it's pretty impressive nonetheless. And D2 is interesting. That's a freewheeling diode, so when you shut that motor off and it spins down, that magnetic field collapses, all that current's got to go somewhere, and that diode lets it freewheel through the rectifier without damaging anything. And then that small connector in the middle there goes to the potentiometer on the front, which is just a voltage divider that's basically setting how much of that AC sine wave is getting chopped off and rectified, and thus setting the speed of the vibrator, and by extension the speed of the motor. The fourth pin on that goes to the rapid switch, and that just bypasses the potentiometer to effectively set maximum speed on the motor. Okay, picking my jaw up off the floor now, let's get that circuit out of there and resume our inspection here. Now the back side of the board is okay. It's been hand soldered, but it's actually not too bad. I've seen a lot worse inside budget consumer electronics, let me tell you. With the potentiometer isolated now, I can run some tests on it. So I've got the meter hooked up, and yeah, you can really see the effect here. As I try to make small adjustments on it, all in the same direction, the readings jump all over the place. Now this is only a 560 ohm pot, but it's jumping around like 100 ohms sometimes. Even though I'm moving always in the same direction, it jumps up and jumps down. It's very twitchy. And this is definitely part of the problem with this thing. It's very hard to set the speed on it, and it changes speed while it's running just with the potentiometer sitting still. You can see the numbers are changing even when I don't touch it. So this thing is definitely flaky. The direction change now is done down here. So the lever arm has a crank pin on it, and it rocks this little kind of cam mechanism back and forth, and that activates these standard industrial micro switches here. There's one on each side, one for each direction. These micro switches are a commodity thing. They're in basically everything. They're a good thing to keep in inventory because just about everything in the world has a bunch of those in it. So let's get a closer look here at that mechanism. This pin comes out here, and I can move this arm out of the way now. I'd really like to get to that potentiometer because I think it needs to be probably replaced. It's so flaky that I don't know that it can be salvaged, and it's the source of a lot of the problems on this thing. So I'm gonna get the knob off of there, and let's see if I can slide this thing out of there. Now it's, okay, so it's attached to this bracket here. So I get this bracket off. It slides out now, but it's not gonna clear that armature there, so I'm gonna have to disassemble things a little further here. So I put that bracket back on, and I'm gonna take that jam nut off. This is a panel mount potentiometer, but they've made that goofy bracket there to turn it into a chassis mount. And so I'm gonna see if loosening that will give me enough wiggle room here. If I can rotate it 180 degrees, I think the wiring will clear that armature. But it won't rotate because the anti-rotation tabs are in place as they should be, so I guess that's good. So I will pry that straight, and then hopefully I can slide it out of the bracket and allow me to rotate this thing. And yeah, nope, that is not going to do it. I think there's another anti-rotation tab on the bottom side of this thing. So unfortunately, the motor is going to have to come out. I was trying to avoid that, so I'm trying to figure out how the motor is installed. The brushes are certainly going to have to come out, so I'll remove those and inspect, and they actually look in good shape, so that's some good news. And well, it looks like these long bolts come out of the cap at the back. It's the only thing I can find that might be holding the motor in. There's no fasteners on the underside or anything below that I could see there with the dental mirror. So off comes these bolts, and the rear motor cap comes off, and that's retaining the rear bearing as well. That's why I was trying to avoid removing this. I didn't want to disturb the bearings if I could help it, but yeah, you know, that's glass fiber reinforced, but it is plastic, so not super confidence inspiring. That's about what you get with a budget open frame motor like this. I can't get the stator out, but the rotor will pull free now, so I'll get that out of the way. You know, it's not super inspiring quality-wise. The windings are not epoxied, and everything is very basic, but you know, it's what you get in this price range. Now I can see down there, and the stator is not attached anywhere that I can see, so maybe just more force is all that's needed. And yep, that is what it needed. I'll remove this zip tie to get some wiring out of the way, and then I can finally get access to the lower anti-rotation tab on this thing. So I can bend that out of the way, and that finally allows me to slide it out of that bracket, rotate it around so the wiring will clear the armature there, and nope, it won't clear. Wiggle that around, maybe just jiggle that, just pull that around the side there and jiggle, angle that, and it, nope, that is not coming out of there. Sigh, got to dismantle this whole thing further. So the dog clutch has a pin through it, and there's a very mighty spring here that I would really rather not mess with. So I don't think I'm going to try to dismantle it from the top side. I'm going to flip things over here. There's really not anything holding that shaft in there except the gear as far as I can tell. So I think that's my vector there, is to get that gear off. So using some parallel jaw pliers on the flat sides of the dogs on the top there, I can then use that to keep the shaft from turning and remove the nut that appears to be retaining the gear. It's just a basic nylock nut here, nothing fancy. I didn't expect it to be tight, and it is not because it is just a plastic gear. With that nut removed, however, the gear does not want to come off, and now my hands are greasy. Get the dental mirror in there again and see if there's something retaining it from the back, maybe a spring clip of some sort. I don't see anything. A little prying on the case doesn't help because it just collapses the clutch spring, so that's no good. Now my fingers are greasy again. Why do I keep doing that? It's not working. I'll see if I can get some rotation out of it here. It might be threaded on, or it might break it loose from the shaft, but no, it will not rotate either. I'm trying to put kind of minimal pressure on things because it is just plastic here. I don't want to push my luck, but yeah, I'm going to have to get out the puller. So I'm going to try to use the puller, but very gently, because again, this is just a plastic gear. So it took some finagling to get the puller on there, but get it on there I did. Once I had it set up, all I needed was fingers on the puller to remove it, so it wasn't tight at all. Now on the back there you can see a channel cut there, and that is what keys it to the shaft. There's a pin in the shaft here that sits in that groove and keys it to the shaft. And now out comes the shaft. How about that? Result. Imperial fist shake of victory, and out comes the potentiometer. That is a long shaft on that thing. Look at that. Significant victory. And it's covered in grease for no good reason. Everything in this thing is covered in grease for no good reason. All right, let's clean it up and run some tests on it here. So again, I got the ohmmeter on there, and yeah, same thing. You can see how twitchy it is. Just touching it causes it to jump around. Now, I did actually spend some time trying to source this thing, and I couldn't find a replacement on DigiKey or Mouser or eBay. This is just a very old style and design of potentiometer that isn't made anymore, which is weird because this power feed is not very old. So it just seems like these Chinese parts sometimes, they don't have a real supply chain. The factories are just buying up lots of old, scrap parts and building stuff out of it. So you can't get the replacements sometimes. So instead I'm going to have a go at refurbishing this one. So I'm going to take it apart here. These little tabs here fold back and you can remove the can. There's really nothing much to these things. It's just a wiper that runs on a carbon disc or a wire wound ring. And survey says carbon disc. You can see how this thing works now. The little piece of PCB there is the wiper. You can see the carbon disc there. So the more carbon that's between the center pole and one of the outer taps, the higher the resistance is on that tap. And then the other tap is the negative, if you will. From this angle, you can see the wipers. They look like little record needles. There's 3 of them there just for improved contact and redundancy. And so you can see how those just slide around on that carbon disc. So a common cause of failure in these is the carbon flaking off or becoming dirty or the wipers being corroded. So I've got an old school fix for that. This is Radio Shack Contact Cleaner. You can't get this stuff, of course, anymore, but this can is about 20 years old, and I don't know what the modern equivalent of it is, but this stuff is great. So spray some of that on there, work it around, let the excess evaporate off. A quick test there, and it does seem better, but it's really hard to say with a multimeter. Multimeters buffer the data quite a bit, so that you can't really get a high frequency read on something without an oscilloscope. But it does seem improved. It's definitely more linear and less twitchy. So I'll put the can back on, reassemble it, and see if it's any better. If this doesn't fix it, well, I'm probably looking at replacing the driver board with a better designed one. One more thing to investigate though are the switches. They're tied together in a block down here, a couple of screws, and that assembly lifts out. Because the thing runs differently in one direction than the other, a possible explanation could be one of the switches being bad. These micro switches fail all the time. It's good to have them around for that reason. So I'll get the multimeter on there and I'll just check the resistance of both switches. Make sure there isn't something dirty or corroded inside there. So I got the continuity meter on there and you can hear that. And then I switched to resistance and I'm checking that. And yeah, the resistance is very low on this switch, about 4 ohms. So I switched over and checked the other side and it's the same. Now these switches are in circuit and you can't actually measure resistance properly on anything that's in circuit because of course I'm actually measuring the motor windings there. However, if the 2 switches were different, it would show here. I'm just looking for evidence of why the thing runs faster in one direction than the other. But the switches both seem fine, so this certainly strengthens the evidence for my neon lamp theory. This assembly also has a smoothing cap stuck to one switch there. It's in parallel across both switches. Okay, I've done what I can do here, so I'm going to reassemble. As I say, I couldn't find anything even close for a replacement potentiometer, so I hope that cleaning that one up improved its performance. And it looks like the directional differences in behavior are down to the circuit design, so probably nothing much I can do about that. But I'm cleaning things up and I'm freshening the grease because what's in here is pretty nasty. Reassembly was the reverse of disassembly, and I'll just feed the wiring back through. The trickiest part of reassembly was getting that big heavy clutch spring aligned between the 2 halves, but a few tries got it done. And put those fasteners back in and let's give it a little test run. Well, it still works. That's good, I guess. It sounds about the same. It always sounded terrible, and well, it still sounds terrible, so I haven't made it any worse. But let's get it under load and see if it runs smoother and better than it did. Back on the mill it goes. It slides down onto the slots, and then the trickiest part is getting the backlash set right. So I just put it down all the way, and then I loosen one bolt at a time and just tap it upwards a little bit at a time until the backlash is correct. You know it's right when you basically can't feel the motor when you turn the hand wheel at the other end, and it should be almost silent. The sweet spot for achieving those goals on spur gears is very narrow, but you can do it, so just keep at it. And I know people have all kinds of tricks for setting backlash on spur gears, like putting a piece of paper between them and whatever. I don't find any of that works for me. I just go by sound and feel. And there you can see how it's barely making any noise, at least in one direction. It makes a little noise in the other direction. Mechanically, this thing is actually quite cleverly designed. Electrically, well, let's just say it's an impressive exercise in cost cutting. And I'll run it back and forth with the power feed and make sure it sounds okay. Basically, the loudest noise should be the motor. You shouldn't hear any noise from the gears, especially when running the rapids. That's a good test to see if you've got the backlash set correctly. So it still runs at a slightly different speed in both directions. However, it does run smoothly in both directions now, which it didn't. It isn't doing that thing where it starts laboring and slowly dying. And now, look how slowly it'll run. I can run it very, very slowly indeed, and it doesn't stall or stop at all. So that is a substantial improvement, I have to say. The speed adjustment on it is now actually quite good. It's very smooth and it doesn't jump around, and I can get it to run very, very slowly, which is going to be great for things like fly cutters. I definitely improved it. I think cleaning up that potentiometer was probably the biggest win here, and maybe swapping out the grease helped a bit as well. Swapping out that neon lamp with a proper diac would probably fix the velocity inconsistency from left to right, but that'll be a project for maybe a future video. I hope you enjoyed this little exploration of a basic import electric power feed. Thank you very much for watching, and if you can swing it, throw me a little love there on Patreon. That's what really helps out the channel the most. And I will see you next time.